I sort of interpreted my role here today as sort of presenting one of the Greenland Climate Research Center projects entitled the Marine Arctic Carbon Cycle, Consequences of Climate Change. It's a project that have about 15 people involved, and it's a 4.5 year long project, and so we are roughly halfway through the project as it is. Our workbench is the marine carbon cycle, and we have posed 4 central questions we think are important to address if we are to understand how the Arctic marine ecosystems are to change with the predicted climate changes. These 4 questions are: how does sea ice growth and melt influence atmospheric CO2 exchange? What are the biogeochemical function of sea ice associated marine microbial communities? And how does changes in sea ice cover affect system production, and how efficiently is carbon in the sediments turned over or retained on long time scales? There's no way I'll be able to cover this in 6 minutes, so what I decided to do was I've just taken 3 small sub-projects out of this overall picture here, and the first thing I want to address is benthic primary productivity. We think that the microalgae primary productivity is grossly underappreciated in the Arctic. There's a vast continental slope with a very high potential for benthic primary production. You can see that from photos, for instance, taken at the seabed up there, covered by benthic diatoms. They are from 30 meters of water depth. We investigate that by a range of many techniques. I'll just focus on one here, and that's our new toy, aquatic AD covariance, which from simultaneous measurements of flow and oxygen variations above the seabed can infer the exchange across the seabed. So we can measure how much oxygen is coming out or taken up by the seabed, and the advantage of the technique is that it takes a very big footprint, more than 100 square meters of the seabed, and we can apply it to very complicated substrates like gravels and stones and rocks and sand and so on, and incorporate that in our understanding of the carbon cycle. The next slide will show one data set from such a deployment from Nipiset Sound at 6 meters of water depth over 5 days. You can see the light at daytime, dark at nighttime, and you get at the same time see the concurrent fluxes measured by 2 instruments deployed next to each other. And you can see you have oxygen release when it's light and upsec when it's dark. From such data sets, you can get excellent quantitative estimates of the benthic primary productivity. Done that in many places. We've done that seasonally, and you can see one seasonal study here from the same site here, where there's clear relation between the net primary production and the light availability. The integrated annual rate here is 220 grams of carbon fixed per square meter per year, and that's immense. It's very high and by far exceeds the pelagic production, underlining how important it is to include them. The AD covariance is really nice tool. We apply it for many other research questions, which I won't go into, but we deploy it to great depth using our benthic autonomous landers, where we investigate things at the deep sea. We use it to quantify exchange of temperature, salt, and oxygen, for instance, between sea ice and water. It's really a versatile tool. The next example I want to give is pelagic primary production. The traditional way of quantifying that is to take discrete water samples and incubate them in a bottle and measure the rate that's occurring in those bottles. Obviously, it's very difficult to sort of get any dynamic responses or to integrate great heterogeneity, which we know exists in many water bodies. And to complement that, we have recently started using AUVs to map out the distribution of prime key drivers for the pelagic production for chlorophyll A, for instance, light and temperature and salinity and so on, but most important, of course, oxygen. So by combining the other measurements with AUV, we can, for instance, profile the water column many times, which is done here from recent data in Maja Fjord in Denmark. And from such data sets, you can get 3-dimensional distribution of the oxygen within the water column, and you can follow that distribution relatively with a high spatial resolution or temporal resolution. And by making some assumptions about exchange at the boundaries, you can then infer the net primary production and integrate big water bodies. Here, for instance, you have water column of 10 meters depth and a transect about 500 meters revisited many times, and you could get the net primary production and thereby get a much better impression on the activity of the system. The last example I want to show is related to sedimentation. We believe that aggregates sinking from the photic zone is grossly underappreciated in understanding the turnover of carbon in the water columns, because many studies focus on the free living microbes in the water column. But essentially there is a lot of carcasses, fecal pellets and agglutinated algae that sinks to the seabed. And together with 2 other projects in the Climate Center, we have asked these two questions: how much carbon and nitrogen mineralization is associated to aggregates, and to what extent the sinking aggregates actually become anoxic when they're sinking through the water column. And you can see example of the aggregates down here. The preliminary data we have been doing actually show that there's a very high oxygen consumption of these aggregates, clearly indicating there's a large turnover of carbon in these aggregates. Using novel sensor designs where we can direct take images of oxygen inside aggregates, we can show that they do go anoxic while they're sinking. And why is that interesting? Well, that's interesting because in the anoxic aggregate we could certainly have other processes ongoing, like denitrification, where the precious nitrate used by the primary producers is converted into dinitrogen and lost from the system. The activity is regulated mainly by the size and the oxygen availability around the aggregates. And we're even including now, and you'll hear more about that later today when Torkel talks, included living copepods in these assessments. And these preliminary data has just led to two very recently newly funded projects that will join the center in January 2012, where we're going to look into how important are these sinking aggregates for the marine carbon and nitrogen cycle, and to what extent, when these aggregates settle at the seabed, do they transform the nitrogen cycle in the sediment. This was just three of the smaller sub-projects within this overall concept of understanding or mapping out the climate sensitivity of the marine carbon cycle. We have a lot of other things ongoing, a lot related to the microbiology and sea ice, to the inorganic chemistry of sea ice, and how important sea ice is in regulating CO2 exchange. We do a lot of effort investigating to what extent carbon settling at the seabed is turned over into CO2, to what extent it's retained in the geological record, and thereby being a sink in the overall carbon cycle. The center is all about synergy and collaboration, and I've just listed here some of the projects which you'll learn more about today as they're coming up, that we have had very active collaborations with. All of them are leading into, either have already led into co-authored manuscripts or manuscripts that are in progress. A synergy and collaboration, I'm sure, that will be expanded to the entire ARC Center in the coming years. And for that, I would like to thank you and the rest of the team from our project. Thank you.